Hello community, so great that you are back. Today we talk to our AI in our car and say, hey AI, do some physics. No, absolutely. Now you know momentum transfer, né? And independent if you have a large multimodal model, a vision language model, a vision language action model, AI does know here momentum transfer and understands here the physics of momentum transfer. Great. But imagine now we have trained this on video training. This AI has seen millions of examples in the real world, thousands and thousands of hours here recorded here for the car. Everything is encoded now here in, let's say, a transformer architecture, but it is the parametric knowledge of this AI, no? A deep ingrained representation of all the universal physical laws it saw during the training, like the conservation of momentum. So you are now on the highway with your car and now something happens. The car, the AI, detects an unseen object and has now to make a decision. What about the reasoning? Let's have a look at this. So, unseen object, this means not in the training data. This could be a real catastrophe because it has no learned algorithm how to deal with this unseen object. How to predict, and we need AI to predict the future, predict the next time frames here if you think about video time frames. So you might ask, hey, how can your AI in your car learn, because you don't want to update here the complete AI here over the air, no? So can AI learn here on the road? Now, a solution might be in context learning, no? You say, hey, you know what? I show here this AI in my car dozens of videos, or it records here videos here of new object. Let's say it's a red car. It doesn't matter at all. It's just an unseen object before. And this object has specific characteristics in its dynamics, in its behavior. It doesn't matter. We just have to learn something new. Like here, you see exactly, you would understand immediately what is going to happen, but an AI that has now to decide for you is not that easy. Because if you approach a critical situation, you want that your AI chooses a minimal impact scenario. So has the AI in your car the power to do this? We have a brand new study, and this is from Michigan State University. Those are the two authors, and they say, hey, for our large multimodal models here, we have now a new benchmark. Large multimodal models struggle in inductive physical reasoning. What a surprise. So they say, but why? Because humans possess here the skill to adapt their physical reasoning to unseen environmental, physical environments from just a few visual examples. If you have seen 1, 2, 3 times here an unseen object before, now you are familiar, now you know exactly what's going to happen. How can we do this with an AI? So we have a parametric physical reasoning. No? This is the LLM ability to answer here physical question based on the knowledge stored in its weight tensor, in the pre-training, everything great. And then we're interested now in inductive physical reasoning. To infer now novel physical laws just from a few video demonstration examples provided here in context, and understand and apply those new behavior, these new laws, to answer a question if we go for the linguistic interpretation, or make a decision if we go here for an AI in a car. Now, the central question now that the authors of today's studies ask, hey, can a multimodal AI switch between the parametric knowledge and its newly learned inductive physical reasoning capabilities by now comparing the physical laws in the examples to those encoded here in the parametric knowledge? What will be the dominant knowledge? Will it override? Will it substitute? Will it just ignore some parts of the parametric knowledge? What is going to happen? So, to test this, they decided we need a new benchmark. We need something new, a synthetic video. Everything is unseen, therefore, and we build a new environment. We build new objects, spheres, cubes. They are colliding. You have simple momentum transfer rules. And this gives now the researcher a new benchmark. And let's see if AI today is able to understand and learn. Now, at first, we have a regular scenario. No? A moving cube hits a stationary cube of equal mass. This is something that the AI learned in its parametric knowledge, recorded this on video scenes, no problem at all. But the real interesting part is, of course, irregular scenarios. This is here the core innovation of this particular paper from Michigan State University. They say, hey, we build our worlds. And I build now a synthetic video of a virtual world where I build now objects that have a very particular behavior. And now I want to see if, take here a standard AI system, if it can handle this. And they said, okay, so we have now different scenarios. Of course, they have to classify this, so let's go with this. The momentum violation scenario. It's an irregular scenario. A moving cube hits a stationary cube of an equal mass, and instead of stopping, it continues with its original velocity as if the other cube wasn't there. You see, absolute an irregularity, but hey, it's just a pattern, so the AI can learn a new pattern. But will it override the parametric pattern? Another scenario, angular momentum violation. Two objects collide head-on, but they begin rotating around their centers of mass. Or you have here only red color object can pass through other objects, but not the blue one. So this tests if the model can bind here a physical property to a visual feature. And this size bias, of course. You have a tiny but very heavy object is deflected now by large but light objects. So let's generate some videos. Let's provide here some learning material and see if this overrides the parametric knowledge of the AI. You know, AI hopefully become more and more intelligent to protect human lives on the street. So your car will have to make a decision. It is not acceptable that your AI is not doing anything at all if it encounters an unseen object. It has to protect humans in the car and the other humans out on the street. So this is a real complex situation. And now let's see how current AI systems do, what predictions they have. So at first we need an evaluation protocol. Great. So as I showed you, we have here the position, the orientation, the velocity of all the parameters here. Then they say, hey, we put this in PyBullet, and then we have simply our matrix. And then we selectively change here velocity or orientation or position or the color of the object or the mass or whatever. And then we just use a Blender to generate here a synthetic video. Absolutely simple. Great. Then you have it. You have all the visual input. And you build here irregular inputs. Now you say, hey, I wanted something is happening that is not expected in the parametric knowledge, but I provide now new learning videos and I want to see if this AI in my car is really able to learn new stuff or not. So we have questions. The first one, hey, how much parametric knowledge do LLMs have about here, let's say, physical laws? And can multimodal models augment here their parametric knowledge if I provide here in-context example, a 3-shot or whatever, if I provide exemplars videos with the new probabilities? And how strong is the inductive physical reasoning happening now? Is the multimodal LLM really sticking here to its parametric knowledge, or is it saying, hey, I learned something new, so now I have to apply this new physical reasoning knowledge, or is it just ignoring the new stuff? And then, and this is the main interesting question for me, if we have it, if we have physical reasoning, if the AI tries to predict here the dynamic of this scene, of all the objects in the recorded scene, how is the thinking process happening? Is it done that the AI goes back to the language world and says, okay, now in language I understand, or does it refer to the visual world? Or is it combining both worlds? How is this reasoning happening if we have a multimodal representation? And can this AI system, let's say in your car, transfer the knowledge that it has, let's say in the language and the linguistic encoding of a physical law? Can it transfer this knowledge, and how does it transfer this knowledge to the visual world where it should predict the next time frames in, if you analyzes here the scene, it identifies all the object, it identifies here all the vectors currently. Can it predict the next video time frames for the next 2, 3, 4 seconds in order to understand the dynamics and therefore make a decision where to steer your car so you harm almost nobody, you are not harmed. This would be here a less impact scenario that we are looking for. So you know what? The author said, I don't know, but let's measure it. Let's do the experiment for this. So let's measure the parametric knowledge, a zero shot here on the regular scenarios. And then we measure here the inductive reasoning after we've given a few short examples, a few short videos here of some irregular scenarios. And then we just measure it. Come on, what's the problem? Let's do it. Results. We have here quite a lot of LLMs, and I know you might say, okay, they have here a gamma 3, a gamma here 12B, a QN 2.5, but one of the latest models are missing. Well, yes, of course. You do not choose the very latest models because at first they are not stable, or you don't want to have problems now that you here clearly indicate that maybe the latest vision language model of a very famous global corporation has some main problems in some benchmark. Ne? You could get some real legal troubles. Ne? So therefore it is, if would say, it is a tradition to go not with the latest, but you go here with the one before, or you go with a Gamma 3, a QN 2.5 and not the QN 3. So you see, you selectively change, or you choose here exactly which model you want to have. And yes, of course, you will not find the very latest actual models because the implication could be significant. So here we are. Different scenarios, great, and you see here 0 shot, and then you have a 3 shot in context learning. And you say, hey, great, look, it's positive, green, yeah. So if we compare now the 0 shot, let's say we have with the last one, this is 51, now we have 70% performance with a 3 shot, great. No, we do have an improvement in performance, and this is absolute fantastic. And then you think, yeah, but wait, and the authors tell her, and all the models that we looked at, those models that achieved above 80% accuracy, this only happened in 6 out of 39 scenarios. Now, this is not so great. 6 out of 39 achieve at least 80%. And if you read the paper and you have a look at much more numerical results, we have here now in quotation, this is here the statement here of the authors. Large multimodals can state universal physical laws in language, but struggle to apply them for the reasoning process. So they know them, but they don't know how to use them. Multimodals also hallucinate irrelevant assumptions about the material. Somewhere in the pre-training there was that a red ball might have here a not spherical distribution of its mass density. You have no idea where this was in the pre-training data, but suddenly now there's an interconnect between those data pieces and your multimodal AI now starts to hallucinate because maybe it found some detailed information from its pre-training that does not belong here, but is made a connection. They say, okay, this further hurts the reasoning process and the hallucination and everything. And we conclude, say the author, that the multimodals memorize the law of mechanics, for example, and can recollect them as a factual information, but fail to apply this knowledge for the physical reasoning in the real world decision making. This is not so great. And I say, okay, now let's evaluate whether our multimodal models can leverage the exemplars and the in-context learning that do not follow the true physical laws. Those are the regular scenarios. So here we go and just enforce the known physical laws. This is not that we contradict anything. We just add more of the same stuff to the training. If you want, this is a continued pre-training. So therefore we get plus 10%, plus 19%, whatever. But now really we hit the road and you say, okay, you know what? What if we go now with irregular scenarios, with the videos we generate, the synthetic videos from Blender, with unseen world, with unseen behavior, with unseen objects, and we only provide here in context learning 3, 4, 5 videos of these new objects, and we hope the AI is learning. And here you have now the differences, and only forget about 0 shot, the 3 shot in context learning, the accuracy the difference of LLM between the irregular and the regular scenarios. And if we have a minus, it means it did not learn the irregular stuff. Now look at this. It doesn't look too good, no? I mean, minus 64. Here, look, a JAMA 3, 4B, almost 0, congratulations. Minus 20, minus 20, minus 18, minus 12, minus 36. So you see, irregular learning is so much more difficult, even in in-context learning. So it's not arriving here at the reasoning process of the AI. It just refers here still to its parametric knowledge and not to the new scenes with the new unidentified objects. It does not learn. Now I might say, but hey, wait a minute here with one particular, look, there's one positive. Yes, we do have a learning. Look, here's learning happening. And I went there and I noticed this and I read in the appendix, no? And they said, yeah, this is a mistake because this apparent inductive physical reasoning is due to the LMMs possessing here the wrong parametric knowledge, and just by coincidence, it gets here a positive result about the angular momentum conversation. And they said, you know what? We calculated now in absolute terms here this for AMC, and you will find this in the Annex B4 of the paper, under the heading Absolute Few-Shot Accuracies in LMMs in irregular scenarios, and here you see AMC is minus 51, my goodness. So, yeah, okay, so this is now the truth. This was just, I suppose they were already in press or somehow, and yeah, they corrected it in the annex. So if you are thinking, hey, look, I found something, well, unfortunately, no, it's not happening. Great. So, no physical reasoning. And now let's come to the main point. No? And they say, the AI is reasoning in language. We know LLMs are working great. No? But what about the vision reasoning part? Or can we transfer the physical reasoning between language and vision? Or is it always falling back to language? And here we have it again, the difference here in a three-shot accuracy in irregular scenarios between video only and video text settings. So if you have the difference, if you have video only and it would be positive, then it learns visual. If you have this difference and it is negative, it only learns language-wise. Okay, look at this. You get a feeling, no? I mean, average, minus 50, minus 35, minus 35, minus 40, minus 36, minus 10, minus 35, minus 40, minus 60, minus 61. Okay. I think the message is clear now. Now, to answer, the authors have made here a screenshot, inductive physical reasoning by your car AI system, with all the senses and all the complexity that we have, yeah? Show a strong language bias, relying primarily on the textual content of the in-context learning exemplars given to answer the question. The presence of language bias questions the trustworthiness of multimodal models in scenarios with unseen physical laws. So, very simple, it just transfers everything back in the linguistic world. It argues in the linguistic world, and this is it. And what you do in the training here in the visual domain is not really in any way the dominant feature for a multimodal model. Now, unfortunately, if you have a look at those papers, now they're already from 2024, and I was hoping that we advance, we are getting better, but you will see the same result was achieved in this paper, and if you have a look at this paper here from the end of 2024, you see they're also here coming to the same conclusion. Well, okay. I want to say the study is really interesting. They give you a lot of details. Just look here. You have a sequence here of visual frames. Great. Here of colliding two objects here. Then you have a system prompt based on your understanding of physical laws. Answer this, and then you have a question. And then you see here the answers given here by all the AIs. And this is great. And just let's focus here on a Google Gamma 3 4B. And it's interesting, look at this, and it has some ideas, But in the end, it is incorrectly because it assumes the object would be addressed before the collision. No? But this is the 4B model, and luckily they have a 12B model. And if you look now at the solution of the 12B Gamma 3, it is correct. So just having this simple example, I would still say, okay, size matters. If we have here the bigger models, just here as demonstrated here in this, the 12B gets it right. Summary. Through the zero-shot and the few-shot experiments here in those scenarios, the authors found that the multimodal models have limited parametric knowledge of universal physical laws, and the multimodal models struggle to apply these laws during the physical reasoning for any real-world decision scenario. Multimodal models demonstrate only a weak inductive physical reasoning, almost non-existent, when exemplars violate the universal physical laws. This means the parametric knowledge the models have been pre-trained on. So the moment you want to add knowledge to your pre-trained vision language model, you run into troubles. Because what knowledge is now overridden with in-context learning? Is it overridden at all? Is it accepted at all? What has a stronger dominance here in the reasoning? All open question, but visibly, given this study, I would say it does not work with unseen objects. And here, the observed inductive physical reasoning also suffers here from language bias. We just reflect everything back to the language, to the LLMs, and relied little on visual inputs in the, 3-shot exemplars given with in-context learning, shedding doubt on the trustworthiness of large multimodal models on visual input. So, as you see here, shedding doubt on the trustworthiness of multimodal models on visual input. This is not what we are looking for, but this is an assessment. So we should understand here the shortcomings. We should understand that this is not it. You should not really trust here the visual input characteristics. But you know what? There's another research error that already started. What a coincidence. People recognized, hey, it's not working, language and vision, in the way that we want it. So they started here a new idea, and I already had a video on this, and it was Stanford who published this, that forget about language. We just will try to teach an AI system vision only. And here in this video, I showed you here the new visual reality AI that is done and understanding the laws of physics here from thousands and thousands of videos. I think in this video it was 1.4 trillion video frames. An AI could build a visual reasoning system, a visual world model without language. So, very interesting here. If you're interested in the technical details, have a look at the video. But this is where we are heading. There are so many shortcomings with our current model. And I know a lot of my subscribers say, hey, why you show us that there are limitations? Just be positive. Just show the positive side. No, the moment it is about safety, the moment you apply this in a real-world scenario, let's say in your car or your product, and you could theoretically only hurt other people or hurt yourself, or there is a responsibility, you have to be absolutely clear what are the limitations of our current AI system. Why is vision not working? Why is everything transferred back here to a language reasoning process? Why is it falling short here of the performance that we are looking here exactly for AI systems in car? We are just at the beginning. If you're kind of interested in this video, subscribe and I see you in my next one.